Good morning, students. Myself, Dr. Eustace Russell, working as assistant professor in the Department of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So far, we are discussing the subject called Engineering Mechanics, subject code of ME25C02 under the regulation of 2025, coming under first year, second semester. So far, we have completed the first two units, that is statics of particles, statics of rigid bodies. Today we are going to see the new topic, that is unit 3. We are discussing with part 1 topics, and in the upcoming slide I will give a glimpse about our syllabus unit 3, and then we'll see about the further topics one by one. This slide represents the unit 3 is nothing but moment of inertia. Moment of inertia, short form it is MI. Syllabus, you can have a glimpse about the syllabus. That is first moments of areas and lines, centroid of composite areas and lines, theorems of Pappas-Guldinus, second moment of area, parallel axis theorem, rectangular and polar moment of inertia of composite areas, radius of gyration, product of inertia, principal axis and principal moments of inertia, mass moment of inertia of the thin plates. These are the various topics we are going to see one by one. Before going on to the topic, we will have a short notes on centroid. What is centroid? We have to look onto that first. Centroid is a point at which the total area is supposed to be concentrated. Normally centroid will be denoted by G with a coordinate of X and Y. Center of gravity is a point at which the weight of the body is supposed to be concentrated. Now this is the basic formula of centroid, that is X bar equal to L1 x1 plus L2 x2 plus upon Ln xn divided by L1 plus L2 plus L3. It goes up to Ln. That is, we can write summation of Li xi divided by summation of L, that is addition of all L. Like that, Y bar equal to summation of Li yi divided by summation of L. For a plane area, we will have x is equal to integral of x dA divided by integral of dA, and yc equal to integral y dA by integral of dA. For composite figures, what I have to do means we have to add all the areas and the centroid OT calculated. That is nothing but xc is equal to a1 x1 plus a2 x2 plus a3 x3 and goes up to an xn divided by a1 plus a2 plus a3 goes up to an. Similarly, yc is equal to also a1 y1 plus a2 y2 plus up to an yn divided by a1 plus a2 goes up to an. Now this is the basic formulas the students must know before solving the problems of centroid. First is straight line, that is nothing but our length is L. Then x bar y bar is nothing but L by 2 cos theta, L by 2 sin theta. Then straight line with the root of a square plus b square the side, then we can write a by 2 and b by 2. The centroid will act like that. Circular wire, that is 2 pi r, everybody knows that. Then r, x bar equal to r, y bar equal to r, otherwise d by 2. Semicircle, pi r, then same radius, then y will be 2r by pi. Quarter circular, the similar thing, pi r by 2, half of that one. Semicircle, half of that one is the quarter circle. Then 2r by pi, both are similar for x bar and y bar. Therefore, circular arc 2r alpha, alpha is in radians, then r sin alpha by alpha, y bar is on axis of symmetry. Then rectangle is important. We have a breadth of b and the depth of d, area will be bd. x bar equal to b by 2 and y bar equal to d by 2. Then triangle is nothing but, we know that half bh, that is b by 3 and h by 3. Then circle is pi r square, then x bar is r, y bar is r, semicircle is r pi square by 2 r, and y bar is 4r by 3 pi. Quarter circle is pi r square by 4, then 4r by 3 pi, x bar also 4r by 3 pi, then y bar also 4r by 3 pi. These are the important formula. The students must know that before solving the problem, these formulas are very, very important. Now we are going to solve one basic problem based on the previous tabular column formulas. Find the centroid of a given lamina as shown in figure. This is one section is given. It is not symmetric one. It's non-symmetric. So we have the various dimension. We have to divide the various sections into 1, 2 and 3. The first section 1 we can see in the right hand side of the slide. We can see what is the sketch. We can tell where the centroid will act. It's a rectangle piece only, half of the distance, that is 110. Then along y axis what we have to do means we have to add all the distances, that is 560 plus 20, that is 580 upon 20. What is the center of gravity of the depth of the rectangle? That is 20 by 2, that is 10. Upon adding you will get 590 mm. X1 equal to 110 mm. Area is nothing but 200 into 20, that is 4000 millimeter square. Now again continuation of the problem. Now we are going to see the second section, that is the middle part. Middle part again the same thing. The y axis we have to add the 20 and the half of the distance of the 560, that is 280. Then we have to find the area, that is 560 into 20, 11,200 millimeter square. X2 is nothing but the width of the section is nothing but 20 only. The half is 10. Y2 is nothing but 280 plus 20, that is we will get 300 millimeter. Then for the third section we can see the lowermost side of the left hand side we have the drawing. We can see the total is 60, right? The total is 60. And what is that width? Width, that is 20. We will take 10 only. Total width is not 60, it is 600, right? It is 600. So it will be x3 will be 300. Finally, applying center of gravity along x-axis, we will see x is equal to a1 x1 plus a2 x2 plus a3 x3 upon a1 plus a2 plus a3, we will get 152.6. Similarly, we are finding yc also, a1 plus y1 plus a2 plus y3 plus a3 y3 divided by a1 plus a2 plus a3, we will get 214.71 mm. Now we will see Pappas-Galdinas first theorem. This is one important theorem. This theorem states that the area of surface of revolution is equal to the product of generating curves and the distance travelled by the centroid of the generating curve while the surface is being generated. That is the important definition. The revolution, the area of revolution. So if you are taking one paper and you are revolve that paper, what you will get? One plain cylindrical object you will get, right? Hollow cylinder. Like that, consider small element having a length of dl and at y distance from xx axis. Surface area dA is by revolving this element dA equal to 2 pi y into dl. That is complete revolution. Now total area we will get A equal to integral of dA, integral 2 pi y dl equal to 2 pi integral of y into dl. Therefore A equal to 2 pi y bar L. Now again continuation of that is based on the area we have seen. Now this is respect to the volume. Volume means we can see this theorem states that the volume of a body of a revolution is equal to the product of the generating area, the distance travelled by the centroid by revolving the area while rotating around the axis of rotation. Consider area dA as shown in figure. The volume generated by the revolution will be dV equal to q pi y dA. Total volume generated by the lamina is nothing but V equal to integral of dV equal to integral of 2 pi y into dA. Therefore, we can write 2 pi y bar a, that is for complete revolution. When the area revolves about theta angle, the volume will be 2 pi y bar a, theta by 2 bar, therefore theta y bar a. Then center of gravity. Center of gravity is a point at which the weight of the body is supposed to be concentrated. Center of gravity exists for solid bodies only. X bar equal to integral of x dw by integral of dw, or we can write integral of x dv by integral of dv. Similarly, we can write for y bar, what you have to do means similarly replace x by y, that's all. Therefore, y by y dv by integral of dv. Similarly, z bar also similar thing, integral of z dv by integral of dv. Now we can see a small derivation part, problem based. Determine a center of gravity of the solid hemisphere of radius r from its diametrical axis. Here we can see in the right hand side, we can see one semicircle image. Consider element. Always you have to take elementary strip. We can see one elementary strip that is taken of radius, that is z, at a distance of x from its diametrical axis. Volume of the elementary strip is nothing but dv equal to pi z square dx. We know that the equation for this hemisphere is nothing but x square plus z square is equal to r square. Upon writing z square is equal to r square minus x square, then dv equal to pi r square. We have to substitute the z square in terms of that equation. Therefore, we will get pi into r square minus x square into dx. Then you have to apply the integration. Upon integration, pi we can take it out. Then 0 to r we have to apply. Then integrate it. What you will get means r square x plus minus r square x minus x cube by x cube by 3. Then you have to apply the limit 0 to r. Then upon applying that x, we are applying r means already one r square is there. It will become r cube minus r cube by 3. Finally, 2 pi r cube by 3. So this is the derivation we have done for the solid hemisphere. Again, we will have the integral of x dv. Again, we have to apply dv. What is the dv? We are having pi r square minus x square into dx. Applying 0 to r limit. Then we will get pi r square x square by 2 minus x4 4 by 4. Limit of 0 to r. Therefore, pi r power 4 by 2 minus r power 4 by 4. Then x bar is nothing but you have to use the formula. Already in the previous slide we have discussed about the formula. Integral of x dv by integral of dv is equal to pi r power 4 by 4 divided by 2 pi r cube by 3. Finally, upon simplification, you will get 3 r by 8. So these are this reference I used for preparing this content. Kindly go through this reference. Thank you, students, for your kind attention for listening this video. I hope everyone understand the concept. So kindly subscribe the channel and share this video to your friends. And we will meet in the upcoming videos with other topics of the same unit. So thank you.